Hi everyone, welcome to Food for Thought. Today we're going to be talking about VSEPR, which stands for Valence, Shell, Electron, Repulsion theory. And this is going to be telling us how different molecules are shaped. So last time we talked about Lewis structures, which show electron configurations. So today we're going to be applying those to determine the shapes of molecules. So, valence shell electron repulsion theory is basically based on the principle that electrons repel each other. And as a result, they will want to get as far apart as they possibly can. Okay? So, we're going to start with the case of two total electron pairs. And I'll explain more about what this means later. So if we have two electron pairs, as in the molecule H2, then we're going to have a linear geometry, right? Because we only have two total electron pairs, and we're going to have those connected, and it's going to be linear. If we have three electron pairs, we have two possible cases. So either we have no lone pairs, and a lone pair just means a pair of electrons that's not used to bond. Because generally, a pair of shared electrons is what bonds. So, pair of shared electrons induces bonding. So, a lone pair is one that doesn't bond. So, if we don't have a single non-bonding pair, like in boron trihydride, we get what's called a trigonal planar geometry. So, we just have everything in a triangle. And I'll show you what these look like. If we have one lone pair, like in sulfur dioxide, we get a bent geometry. If we have four total electron pairs and no lone pairs, we get a tetrahedral geometry. So we have the carbon atom in the center surrounded by the four hydrogens in methane. If we have one lone pair, like in ammonia, NH3, we're going to have a trigonal pyramidal geometry. So the nitrogen in the center surrounded by the three hydrogens. And if we have two lone pairs, like we have in this water molecule here, we'll get a bent geometry, because the two electron pairs will repel each other, causing the molecule to bend. If we have five total electron pairs and no lone pairs, like in phosphorus pentachloride, we'll get a trigonal bipyramidal geometry, which is hard to visualize, so I'll draw you a picture later. If we have one lone pair, like we have in sulfur tetrafluoride, then we're going to end up with what's called a seesaw geometry, because it sort of tips on its side. If we have two lone pairs, then we'll get what's called a T-shaped geometry, like in bromine trifluoride. So two lone pairs up here sort of balance the whole thing out. They repel each other, but they don't have any net effect, so we get a T-shape. And finally, if we have three lone pairs, they'll again balance each other out, and we'll have a linear shape. Our last case is if we have six electron pairs. If we don't have any lone pairs, we'll get an octahedral geometry. So we'll have the sulfur in the center, and then the six fluorines at the vertices of a regular octahedron, like in sulfur hexafluoride, which is a very heavy gas, heavier than air. If we have one lone pair, then we'll have what's called a square pyramidal geometry. And finally, if we have two lone pairs, then we'll have a square planar geometry. So here are some things to remember. The number of lone pairs is only based on the central atom. So note, we didn't count the total number of electron pairs, because if we were going to count the total number of electron pairs in sulfur hexafluoride, for instance, we have 6 around sulfur and then 3 around each of the fluorines. So that would make 24 total, and we don't need that many. We're just counting what's around the center atom, because that determines the geometry. And then also, what we're going to call the electron geometry is basically the geometry of the molecule if it had no lone pairs. So no lone pairs is going to be the electron geometry. And if you go back in the video, you'll see I've underlined these for each case. So we have linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. And each subcase, so the more lone pairs we add, we're basically just taking an atom away from each of these geometries. And you'll see that each of these geometries get smaller. So let's try drawing some of these. So let's start with the very simple case of 2 total electron pairs and a linear geometry. So this is going to be pretty easy to do. We're just going to have a hydrogen atom, another hydrogen atom, or we can do something else that's linear. We can do CO2. So we're going to have 4 total electron pairs, none of which are lone pairs, so we have a linear geometry. And so we can see pretty easily from these that all of the angles are going to be 100 degrees. Now, if we want to take something like trigonal planar, so we'll do our boron trifluoride. We're going to have boron, and then the 3 fluorine atoms, like that. And our trigonal planar geometry is going to be 360 degrees over 3, and that's going to give us central angles of 120 degrees. Now, for a tetrahedral geometry, a tetrahedral angle, the center angle of a tetrahedron, is going to be 109.5 degrees. And you're going to want to remember that. So if we have a tetrahedral geometry, we're going to have something like methane. So C, H, 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 and then 1 going back into the page, which we denote with a dotted line. This is going to be 109.5 degrees. Now, what if we wanted to have something like a trigonal pyramidal? So trigonal pyramidal, let's say like ammonia. So trigonal pyramidal, something like ammonia. So we're going to have our nitrogen and then our 3 hydrogens. And I'm going to draw in the 1 lone pair up here because I think it's important. So normally, if this were a tetrahedron, we'd have a 4th atom up here, and all of the angles would be 109.5 degrees. However, since we only have a lone pair and not an atom, that lone pair is contributing some extra negative charge, which pushes all the negative charges in the other atoms away. So as a result, the other atoms are going to get closer together, and the angles are actually going to be something less than 109.5 degrees. And it varies with what exactly those atoms are, which will be discussed in a later lecture about electronegativity. But it just depends how the charges are shared, but it's always going to be less than 109.5 degrees. Similarly, a bent geometry also always going to be less than 109.5 degrees because they're, again, lone pairs. So if we had a bent geometry, let's say water, H, O, H, with our 2 lone pairs. Those 2 lone pairs are going to push the hydrogens away. They're going to get close together. And we're going to have, again, less than 109.5 degrees. Now, let's look at a trigonal bipyramidal structure. So trigonal bipyramidal is a little bit hard to visualize. So bipyramidal is going to give us something like this. So we're going to have, where it's going to have phosphorus pentachloride. Cl, Cl. And you'll note in the earlier pictures I've started denoting bonds just as lines instead of pairs of shared electrons because you guys have seen that often enough. So we're going to call the angles between the 3 chlorines that are all in one plane, we're going to call those equatorial because they're on the equator of the molecule, it's symmetrical. And those are going to be 120 degrees, again, because we have a triangle and it's equilateral. And then the other two chlorines are going to be in a perpendicular plane, which is going to be axial. We're going to call that axial. And since they're perpendicular, the angles are going to be 90 degrees. Now, similarly, in all the other geometries based on the trigonal bipyramidal structure, the more lone electron pairs we have means that we're going to reduce the angles. So if we had, for instance, a seesaw, so we're going to have something that looks like this. Doesn't really matter what we have here. So note if you stood this on its end, it would look sort of like a seesaw. It would balance. So we'd have less than 120 degrees equatorial and less than 90 degrees axial. And of course, again, for our linear geometry, we'd have 180 degrees because it's a line. Now, finally, we are going to have our octahedral structure. And this is actually not going to be that difficult to visualize. If you guys have seen, for instance, like Dungeons and Dragons dice, it's a regular octahedron. So if we're having, say, sulfur hexafluoride, we're going to have 4 atoms here this time. I should probably have drawn these all as dotted lines, but that's okay. So if we have our 6 fluorine atoms, now we would have different angles for the equatorial and the axial, but notice how all of these fluorine atoms are in a square. And since we know that 360 over 4 is 90, it turns out that in fact every single angle is going to be 90 degrees. So thus our square pyramidal geometry, which is just this but with one atom removed and replaced with a lone pair, is going to have less than 90 degrees. And then finally we have our square planar, which is going to look something like this. Don't really worry about what this is. And again, this is now the octahedral, but with 2 atoms removed. And since they're both replaced with lone pairs, they exert equal and opposite effects. So we're again going to have uniform angles of 90 degrees. So that's just a brief introduction into valence shell electron repulsion theory, and this illustrates how we determine the shapes of molecules. Next time, we're going to talk about more about the properties of these molecules by delving into periodic trends and how location on the periodic table influences the character of an atom. See you then!